Chemical reactions. Reactions of haloalkanes can be divided into three categories. The first one is nucleophilic substitution reaction. The second one is elimination reaction. And the last one is reaction with metals. Click on their corresponding buttons. Nucleophilic substitution reaction. Let us now understand nucleophilic substitution reactions of haloarenes. Aryl halides are extremely less reactive towards nucleophilic substitution reactions due to the following reasons. The first one is resonance effect. In haloarenes, the electron pairs on halogen atom are in conjugation with pi electrons of the ring, and the following resonating structures are possible, which can be seen in the given figure, which shows resonance in chlorobenzene. Negatively charged species is capable of donating its electron to an electrophile and is known as nucleophile. Example, OH-. Groups like cyanides and nitrides possess two nucleophilic centers and are called ambident nucleophiles, and therefore can act as a nucleophile in two different ways, in which one of its nucleophilic center is carbon and in the other one its nucleophilic center is nitrogen. That is, linking through carbon atom resulting in alkyl cyanides and though nitrogen atom leading to isocyanides. A negative charge species can act as a nucleophile or base. Nucleophilicity is ability of the species to act as electrophilic carbon, and basicity is ability of the species to remove H+ from an acid. Nucleophilic substitution is found to proceed by two different mechanisms. SN1, unimolecular nucleophilic substitution reaction. SN2, bimolecular nucleophilic substitution reaction. Click on the corresponding buttons to learn more. This reaction occurs in two steps. Step 1 is the polarized CBr bond undergoes slow cleavage to produce a carbocation. Consider the reaction CCS3 Br reversible CCS3 plus Br minus. This reaction involves one step only and occurs through a transition state. OH- plus CS3Cl gives CS3OH plus Cl-. The reaction takes place simultaneously and no intermediate is found. The reactions involve second-order kinetics. That is, the rate depends upon the concentration of both the reactant. That is, rate is equals to K times concentration of CS3Cl multiplied by concentration of OH-. In general form, rate is equals to K times concentration of Rx multiplied by concentration of nucleophile. As the reaction progresses and the bond between the nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. Orange dot represents the incoming hydroxide ion and green dot represents the outgoing halide ion. As this happens, the configuration of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind, while the leaving group is pushed away. This process is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group, and such structures are unstable and cannot be isolated. This is because the carbon atom in the transition state is simultaneously bonded to 5 atoms and therefore is unstable. You can here see a transition state of CS3OHBr. This reaction involves one step only and occurs through a transition state. OH- plus CS3Cl gives CS3OH plus Cl-. The reaction takes place simultaneously and no intermediate is found. The reactions involve second order kinetics. That is, the rate depends upon the concentration of both the reactant. That is, rate is equals to K times concentration of CS3Cl multiplied by concentration of OH-. In general form, rate is equals to K times concentration of Rx multiplied by concentration of nucleophile. As the reaction progresses and the bond between the nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. Orange dot represents the incoming hydroxide ion and green dot represents the outgoing halide ion. As this happens, the configuration of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind, while the leaving group is pushed away. This process is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group, and such structures are unstable and cannot be isolated. This is because the carbon atom in the transition state is simultaneously bonded to 5 atoms and therefore is unstable. You can here see a transition state of CS3OHBr. Stereochemical aspects of nucleophilic substitution reactions. A SN2 reaction proceeds with complete stereochemical inversion, while a SN1 reaction proceeds with racemization. We need to learn some basic stereochemical principles and notations. The first one is plane polarized light and optical activity. Certain compounds rotate the plane polarized light produced by passing ordinary light through Nicol prism when it is passed through the solutions. Such compounds are called optically active compounds. If the compound rotates the plane polarized light to the right, that is clockwise direction, it is called dextrorotatory or the D form and is indicated by a positive sign. If the light is rotated towards left, that is anti-clockwise direction, the compound is said to be levorotatory or the L form and is indicated by a negative sign. Such plus and minus isomers of a compound are called optical isomers, and the phenomenon is termed as optical isometry. The second one is molecular asymmetry, chirality, and enantiomers. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. Enantiomers possess identical physical properties, namely melting point, boiling point, solubility, refractive index, etc. They only differ with respect to the rotation of plane polarized light. If one of the enantiomer is dextrorotatory, the other will be levorotatory. The third one is retention. Retention of configuration is the preservation of integrity of the spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation. The reaction taking place is CABCX in presence of Y minus gives CACBY. Consider as an example the reaction that takes place when levo 2-methylbutane-1-ol is heated with concentrated hydrochloric acid. The reaction taking place is CHCS2OH CS3 CS2CS3 plus HCl in presence of heat gives CCS2Cl H CS2CS3 CS3 plus H2O. That is dextro 1-chloro-2-methyl-butane. The fourth one is inversion, retention, and racemization. There are three outcomes for a reaction at an asymmetric carbon atom. Consider the replacement of a group X by Y in the following reaction. If A is the only compound obtained, the process is called retention of configuration. If B is the only compound obtained, the process is called inversion of configuration. If a 50-50 mixture of the above two is obtained, then the process is called racemization, and the product is optically inactive, as one isomer will rotate light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanism by taking examples of optically active alkyl halides. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. Levo 2-bromooctane is allowed to react with sodium hydroxide. Dextrooctane-2-ol is formed, with the OH group occupying the position opposite to what bromide had occupied. The reaction taking place is CHBrCS3 C6H13 plus OH minus gives CCS3H C6H13OH plus Br minus. Thus, SN2 reactions of optically active halides are accompanied by inversion of configuration. In case of optically active alkyl halides, SN1 reactions are accompanied by racemization. Actually, the carbocation formed in the slow step, being sp2 hybridized, is planar, that is, achiral. The attack of the nucleophile may be accomplished from either side, resulting in the mixture of products, same configuration and the other having opposite configuration. This may be illustrated by hydrolysis of optically active 2-bromobutane, which results in the formation of dextro butane-2-ol and levo butane-2-ol. Reactivity of alkyl halide towards nucleophilic substitution. For a given alkyl group, the reactivity of the halide, that is Rx, follows the same order in both the mechanisms. The reactivity of Ri is greater than Rbr, greater than Rcl, which is very greater than Rf. This is because stability of X minus is in order I minus greater than Br minus greater than Cl minus, which is very greater than F minus. For SN1 reaction, greater the stability of carbocations, greater will be its ease of formation from alkyl halides and faster will be the reactions. Thus, due to high stability of carbocations, 3-degree alkyl halides undergo SN1 reaction. Reactivity towards SN1 reaction follows the order 3 degree greater than 2 degree greater than 1 degree. Since SN2 reaction require approach of nucleophile to the carbon bearing the leaving group, the presence of bulky substituent on or near the carbon atom have dramatic inhibiting effect. Thus, 3-degree halides are least reactive towards SN2 because bulky group hinders approach of nucleophile. Reactivity towards SN2 reaction follows the order 1 degree greater than 2 degree greater than 1 degree, which is opposite of reactivity towards SN1 reaction. Allylic and benzylic halides have high reactivity towards SN1 reaction because of stability of carbocation by resonance.